All right, so we're going to talk about critical numbers. And critical numbers are going to be something that we use as a reference to start finding maxes and mins and where graphs change direction, that type of thing. So first of all, you always want to look at your function and find out, is your function smooth? So remember, at this point, if you're seeing some radicals or roots, you should recognize that that's probably going to lead you to a cusp, which means it's not going to be smooth. So if we see radicals, we should acknowledge that right up front. The next thing is it continuous? And that's going to be if we've got variables and denominators at this point. If we have variables and denominators, we got to watch out. However, be very careful, because a critical number cannot be where your function is undefined. So for instance, if I have a 1 over x minus 4, my function would be undefined at 4 because I can't divide by 0. But 4 is not a critical number because this function does not exist at 4. So the only places that we're going to have critical numbers are where I may have a cusp, and then when my function's derivative equals 0. So what we'll do is talk through each one, and is our function smooth? Is our function continuous? And does our function's derivative equal 0? And what happens when it does? And so along that line, what we're going to be working with is called Extrema. And Extrema is the plural of extremum. So I could have maxima, which means multiple high points. I could have minima, which is multiple low points. Or I may have one of them. If I have one of those, it would be a maximum. If I have one of these, it would be a minimum. And I'll be able to figure out what those are as we take this little journey through 3.1, which is applications of derivatives. So what we want to look at this point is the last part is going to be absolute and relative. So an absolute max or an absolute min will be the very tallest point or the very lowest point, where relative maxes and mins can be all of the hills and valleys along the way. So all tall points and all low points. It's just that the tallest of them should be the absolute max, and the lowest of these should be the absolute min. Now the only issue is the absolutes can include endpoints. Okay? The relatives cannot include endpoints. Okay, so for 3.1, what we're going to do is start putting all this stuff together. So I want to find out if I've got maximum values, minimum values, and all that kind of good stuff. So if we look at number 1, it says, find the value of the derivative if it exists at the indicated extremum, which means that is a low point on the graph or a high point. If I look at this picture, I see it's a low point. So I'm looking for a minimum. And because it says extremum, that is singular, so I'm looking for a single low point. So basically, I want to know the value of the derivative at 0, which is also saying what is the slope of the tangent line at 0 for this function. So if I grab my function, which is f of x equals x squared over x squared plus 3, that is my function. Well, now what I would need to do is take a derivative. So first of all, before we start this process, is it smooth? So do you see any radicals? No. Is it continuous? Can I make my denominator equal 0? Well, if you try to, you're going to find out that you have to take the square root of a negative number, which is imaginary, so it is impossible for this denominator to equal 0. So we have addressed a couple of things. Is it smooth? Yes. Is it continuous? Yes, because there's no place where my denominator equals 0. So now what I want to do is take a derivative and evaluate it at 0, because again, that's where my attention is being called to, is this low point. So my derivative, I'm going to have to use quotient rule. So I've got the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So notice that your denominator just now has a square on it. So it's still not undefined. It didn't just miraculously change where all of a sudden I can use values that I couldn't use before, or vice versa. So it's still continuous. It's still continuous. Okay. The only way to make a fraction equal 0 is for its numerator to equal 0. But I just said that wrong. What we're doing is evaluating at 0. So I'm going to clean this thing up. So I'm going to distribute my 2x. So I have a 2x cubed plus 6x minus 2x cubed over x squared plus 3 squared, which means these reduce out. And I'm supposed to evaluate this at an x value of 0. So if I shove in a 0 into my derivative, what I'm going to get is 6 times 0, which is 0, over 0 squared plus 3, which is 3, squared, which is 9. So I get a 0. So what you found out is that the value of the slope at 0 is 0. So you have a horizontal tangent line at that minimum. So your answer here is just 0. So now I would like to know the next one. Find the value of the derivative, if it exists, at the indicated extremum. So they gave me a point this time because it's not so obvious to see. I want to evaluate my derivative at a negative 2/3. So my function is a negative 3x times the square root of x plus 1. So I have a negative 3x times the square root of x plus 1. And so I'm going to have to use, remember this is square root. So one of the things you should notice is I've got a radical. Now if you look at this, you have a cusp right here. It's a vertical tangent line. Okay? So I'm allowed to use negative 1 because negative 1 plus 1 is 0. The square root of 0 is 0. And 0 times all that stuff is 0. Okay? So if I shove in a negative 1, I get a 0. I'm allowed to use negative 1 in my original function. So now let's see what happens. If I take a derivative, which I'm going to have to use product rule. So I've got the first times the derivative of the second plus the second times the derivative of the first, which is negative 3. Okay, so I'm going to clean this up just a tiny little bit so it's easier for us to look at. If I have a negative 3 times x, he's in my numerator, over 2 goes to the denominator. This negative is a square root in my denominator. And then I have minus 3 times the square root of x plus 1. So when I look at this, all of a sudden I notice up here I could use negative 1. So x equals negative 1 was okay to use in my original function. But x equals negative 1 is not okay to use in my derivative because it will cause me to divide by 0. So in my derivative, x equals negative 1 is off limits. So what that means is I have a cusp there. If my derivative, or the formula for slope, for a tangent line, or the formula for instantaneous rate of change, is undefined, that means you have a vertical tangent line right there. Okay? You'll have a vertical tangent line. Now, that's not what we're interested in. We are interested in negative 2/3. So if I evaluate at a negative 2/3. And then I have a 2 times a negative 2/3 plus 1 minus 3 times a negative 2/3 plus 1. I'm going to get a negative 6. I'm sorry, a positive 6. So negative 3 times negative 2 is 6 over 6. So that just ends up reducing out. And then I will have a 1 over the square root of 2/3 plus 1 minus 3 times the square root of 2/3, negative 2/3 plus 1. So this is going to end up being 1 over the square root of 1/3 minus 3 times the square root of 1/3. So if I get a common denominator, I can multiply both sides, or top and bottom over here, by root 1/3, or I can clear my equation of fractions. Either way, what you're going to end up getting is a 0 there. So what does that mean? Come back over here. At a negative 2/3, you have a horizontal tangent line. So the value of your derivative, which is the formula for slope or instantaneous rate of change, is going to be 0. So I'm going to let you do that part. All right, so here I have, now, I have an indicated extremum. So if I'm looking at this, I see that I have absolute value. And I also see that he's been flipped upside down and shifted upwards 4 units. So my extremum is going to be a max because it's a tall point. But what do I know? I know that I cannot evaluate the derivative at a cusp. So if you look at your derivatives and integrals sheet, you have a formula for what this is. So I'm going to take the absolute value of some function. So if I have the absolute value of x, the derivative of 4 is 0 minus. And then what does this say? This says take your original function, which is 0, or I'm sorry, which is not 0. Good heavens to Betsy. Which is just the argument over the function as it stood in absolute values. So he's absolute value of x. And then times the derivative of the inside, which is going to be 1. So this is my derivative. Well, what happens if I evaluated it at 0? I end up with a negative 0 over 0, which we learned before is indeterminate. And that means that I cannot evaluate because I can't divide by 0. So what we have here is this does not exist. I cannot evaluate the derivative at a cusp. Okay? So now we are just going to look at pretty pictures for a few minutes and see where to go from here. Actually, we're going to pause and I'm going to pick up later. All right, so we're going to pick up at step 2.